Yeah, I promise this one will be more painless than the other ones. Partly because it already comes with data built in. So in your short course materials, this time I'll actually try to remember. If you're running it in MATLAB, just run the, make sure you're running the .m file. I will run it in, I will run it using the application. So Hafnium plotter 107 or 1.70. Again, the first time you open these, it usually takes a couple of minutes. Okay. And so if you don't see a plot right away, then something probably went wrong. And just given the time considerations, if you did, we can either talk about that after the course, or you can send me an email and say, hey, it never worked for me. What's going on? Either way is cool with me. So here's Hafnium plotter. And so what on earth are we actually looking at? Looks like a little like rainbow colored mountain, right? And so what I thought I'd do first is try to just by example explain what's actually going on here. So what this is if you think about a, let's see, actually, no, I think last year I did this. Sorry, I thought, let me pull up a quick talk actually. This will just be easier to talk about. This is a talk I gave a couple of years ago, but has a nice visual. I'll put this into the short course materials. I hadn't planned on doing this, but it really helps explain what the heck is going on with what we're trying to visualize. So we just spent a lot of time. You can all see this screen, right? This dark screen with one data point. Give me a holler if yes, because I can't see anybody.
Yes, you're good.
Cool, thanks. So we've been looking at a lot of Hafnium data. Sarah just had a lot of fun interpreting that data along with people. And so one of the challenges with Hafnium is you'll have these long stretches of data, these strings of data, these pull downs, as she called them. So visualizing data density can be really challenging. And so what we can do is if we think about one single data point, we can think of that in terms of a distribution, just like we did with age distributions. Of course, the distribution on the epsilon Hafnium axis really isn't very meaningful, right? It's not as meaningful as the one on the, as time on the x-axis as it is on the y, because Hafnium is an evolving system, right? So what we can do instead is just turn that one data point into what we term a bivariate kernel density estimate. And so this is a kernel density estimate in 2 dimensions now for that time in this 2-dimensional space. And what we're actually looking at here is just, you can think of it as a 3-dimensional volume. It's a 3-dimensional Gaussian curve that's based on 2 dimensions of data. We talked a little bit earlier about PDPs versus KDEs. Due to computational intensity, we really have to specify a kernel bandwidth. So we have to assume, as you'll see in just a minute when we play around with the plotter, you have to assume an X kernel bandwidth and a Y kernel bandwidth. And the reason for that is we're not actually making individual little Gaussian curves out of every data point. The mathematics behind it actually involve taking a scatter plot and doing an inverse cosine transform to it and applying the Gaussian covariance matrix to it. So if you want to know more about that, I've written up a little spiel in the hands-on step-by-step guide. But at the end of the day, you can think about it as if you, mentally you can think about it as if you take every data point, convert it into a Gaussian, add all of that together and normalize. That's more of an intuitive way to think about it, but mathematically, what's going on in the background is actually a little bit different. So just like a regular 1-dimensional distribution, you can think about it as the sum of all of the Gaussian curves. Just instead of 1-dimensional lines, now they're 3-dimensional volumes that you add up and normalize. So going back to the plotter, so when you open it up, it'll be in 3 dimensions like this. I like to visualize this in 2 dimensions because it's a little bit, perhaps more, it's a little easier to interpret what's actually going on. So the first thing I want to do is change the kernel bandwidth. Okay, so the kernel bandwidth is the top left here. By default, it figures out what is an optimal kernel based on a diffusion algorithm that sits in the background of the code, and it says, well, based on your data density and distribution, I think this is how big it should be. And you can see that it actually does a pretty good job for this particular data set that's built in to the software. But I like to actually set the kernel. So if you click on this radio button, set, and as you'll see, unlike the rest of the programs that I've shown, this is more of an active program where anything you change, it will just do it right away. So that's what perhaps contributes to the procrastination aspect, George. So yeah, just for demonstration purposes, let's now change the x-axis to a smaller kernel bandwidth. So let's go to 2 and just press enter, and you'll see what it does to the distribution. You see it squishes it all because our 3-dimensional Gaussian is getting narrower on the x-axis. If you make it even smaller, so 1 million years, it's smaller and smaller. You can go crazy with this, and it'll. This is why it can get. You can kind of lose some time doing this. So I think 4, 3, whatever. It's really you're just trying to get a sense of the density of the data. These are arbitrary parameters, a lot or very much like a kernel density estimate for just uranium lead data. We can make it a huge kernel, and then it just kind of washes everything out, and you really can't say anything. So you can either go with the optimized kernel as a guide and then start playing around with what is a good kernel, but really you're just trying to get a sense of where are the dense pockets and where are the not so dense pockets of data. You can do this also with the y-axis, of course. So now you'd be changing the epsilon bandwidth. You can think of that as an assumed uncertainty in your epsilon space. So if you say, well, maybe 2 or 3, and you see what it's doing to the data, the bivariate kernel density estimate, it's just stretching it out along the y-axis. Go 40, go 400, just go nuts with this, right? Clearly, 2 was not so bad. So I'm going to stick with 5. And again, you can think of these as uncertainty for your x-axis and y. So in this case, it's age and epsilon hafnium. But this doesn't have to be age and hafnium data. It can actually be anything. Maybe you had like age and grain size. You can actually just write that in there. And now you notice on the y-axis, that'd be grain size. And you can make the font a little bigger, make it bold. Again, this is all kind of, you can do just about everything that this program does on the fly. This is epsilon hafnium data time t, so that's what we're actually plotting. So I'm going to leave that on there. An important one here is it doesn't actually scale the axes automatically. I will have that in the next version because I get quite a few emails about this. But usually, if your data doesn't fall within the range that's automatically plotted, which is 0 to 200, it won't do anything. So if I went 0 to 0, it's going to say, hey, I don't have any data in there. I don't know what to do. But you notice the data read-in, which is here. You have X and Y that are outside of these ranges that are automatically plotted. So what it does is it'll take this data read-in and then it'll filter everything out that's outside of these ranges for X and Y. And by doing that, it doesn't bias this kernel density estimate, but rather it uses only the data within the window that you actually care about. And so with that, now you can change this to anything you want and start considering wider spans of data. So this is actually a detrital data set from the Altiplano in the Central Andes, and it has data points all the way out to 3 billion years. Now you immediately notice, hey, wow, maybe 5 is a little narrow for our kernel bandwidth right on the x-axis. So again, just kind of play around with it and see what starts informing you about data density. And also, this is an Andean data set, so it's going to be dominated by young grains. Maybe you don't care about those particular grains. You can just chop them off very easily by saying, you know what, I don't really care about the Andean arc. I want to know everything that happened before it. And so now you're looking at just 200 million years to 4.5 billion. And again, all of this is, you can just do all of this on the fly. And that's basic parameterization. You can load in other data. So if you go to load data, maybe you don't care about the Andes, maybe you care about a global compilation. So I've included one of my favorite papers ever written. Elena Bellasilva wrote a fantastic paper in 2010, and she compiled a lot of data. And so in the input data examples, I've included Bellasilva's 2010 zircon compilation for the entire world. And this compilation, now actually this compilation is quite small compared to what's been done in the last 10 years. But this is everything that Elena could find and her team could find globally for all igneous and detrital zircon. So now you see, like, wow, it's probably a bit much to look at in 2D, but if we look at it in 3D, you can use these tools in the top left and start to move this around and try to get a sense of, again, all you're trying to do is get a sense of the data density. So globally, in most rocks and zircons, globally, there's this huge pull down around the late Neoproterozoic, and that's been the subject of ongoing debate in the last, say, 15 years, and it's continuing today with some really interesting models out there. But you see some of the data is kind of truncated, so you might need to increase your axes, and if you're dealing with the global data set, it might take a sec to plot, but just give it time. So how about -40? So we're starting to see the data. We're showing a scatter plot on here, and it's a scatter plot that it's laid on top of this density plot. But maybe you don't want to see the scatter plot because you're looking at Elena's huge global database and you can't actually see what's going on. You can turn that off by turning off this 3D scatter plot here. And so now we're seeing a visualization of the data density for a global compilation, so a global record. And notice how this huge pull down still stands out, even in the global compilation. So you might say, well, wait a second, we were talking about evolution lines. What happened to Chur? Where's all that? That's here in this evolution lines panel. You can plot Chur. You can change the color of Chur if you like. How about magenta? You can make it really, really thick if you want. Really thick line. That's a lot of Chur. You can add your depleted mantle there with uncertainty. Maybe 10 was a bit much for thickness. And then I've added 3 separate options for crustal evolution paths, depending on what you're used to reading or which author you want to follow. I like to plot all 3 just to get a sense of kind of about what is the maximum age of the crust or required age of melted older crust to produce what we're looking at now. Basically the questions that George and Sarah talked about in the last couple of modules. So you can move this around it's pinned right now at 1,000 million years. And so I'm just going to use the middle one actually, just to have one line to look at. And let's move that back to say 2,000 million years. And now you can track, say you had some data down here, say, well, what is the age that is required if it was a 1-stage melt, right? And you can start addressing these questions just by moving around your crustal evolution line. Say you wanted to get after this density part right here, this density mode. So let's bring this up at about 2,200 million years. Yeah, almost got it, right? So maybe 2,300. You see what I'm trying to do here? I'm trying to intersect that mode with the crustal evolution line. maybe blue is probably not good, magenta. So here's where the color map, like, you know, we're especially if you're colorblind, this jet color map is terrible for you to look at. It doesn't work, basically. So I've included a lot of different color maps here that do work better with if you're colorblind or if you just want something a little psychedelic, or hot versus cold, maybe the surface of the sun here. Nice ones, actually gray is really nice if you wanted to then change your lines to, and I'm clicking through really quickly. I encourage you to do the same. Don't try to click everywhere I'm clicking. It's pretty interactive, but you can start to get a sense of the different maps that you can plot. If you're in the States and you're feeling particularly patriotic, you can do that as well. Flag, prism, some of these are less useful than others, but I just thought I'd just include all of the available ones from MATLAB. And in the new version, I found some color maps that are specifically designed for people that are colorblind. So there's a whole color set that's designed specifically for those folks. So those will be in the new version. But yeah, alternatively, you don't even need to plot a map. You can just you can use this to plot a scatter plot. And say you wanted to calculate like running averages. You'll probably see this, you do see this in the literature quite a bit. Like, say you wanted to quantify that. I'm going to turn off the crustal evolution line, and I'm going to calculate a running mean through these data. You can do that by turning on running mean. And what this is going to do is it's going to say every 20 points, I'm going to calculate the mean across X. And I'm going to make it plotted red. Let's plot it in green instead. Whoops. And there it goes. You could maybe red or green was maybe not the best. How about blue? Blue might be good. Yeah, you can see that. Contrast is a big challenge in bivariate space with these types of plots, but you can smooth that out by saying, well, how about take it every 200 points? And well, it's hard to see. Well, let's make it a little thicker, about 5. And you could start to use this. You can also do a running median, and you can maybe set it up the same way. And I like to use medians for most things. They tend to skew the mean. Means are very easily skewed with outliers. Medians are not. So it's good to compare the differences. So how about magenta? That'll be fun. 5. And so in magenta, see the median is a little bit different from the mean. And the reason is it's going to follow the data density a little more closely, because these mean values in blue here at about 700, 800 million years, they're skewed by these random outliers out here, whereas most of the data density at that time, from whatever contribution that was from, it's a lot of depleted mantle, right? A lot of very juvenile materials. I included polynomial fit. This is pretty useless. Actually, I'm going to remove it and add something new, like a standard deviation window would be good. But when I first made it, I threw everything at it that I knew about. So I wouldn't really rely on a polynomial fit. It doesn't really tell you much. Turn those off. Another fun one. If we go back to the map, I'm going to turn off the scatter plot and do a running mean based on the peaks. So those are our peaks, right? And so the DM and chur are going to sit over the top of everything. They're not going to lay on top. I'm going to build that in the future, but this is kind of a fun one. You do a running mean of the peaks. And this is a bizarre plot. But what it does, let's make it a little thicker. It's kind of like if you didn't have a topo map and you were out there trying to pick the most difficult hike you could possibly find, you're going to try to find all the peaks and run up and down them. That's what this is doing. It's taking a mean of all of the highest points along that Y interval. And you can compare with median. So again, this might not be the most useful thing, but I think it might be informative in some cases. Because if you run a mean and median along the peaks, you'll notice that it might look a little different from the actual data itself. So in 3 dimensions, this is more focused on data density based on the map, and peaks in data density, whereas the 3D scatter plots are using they're not using the bivariate kernel density estimate at all, only the scatter plot like you would do in, say, Excel. So lots of fun little things you can do with this. One thing I haven't talked about is contours. If I drag this up into 3 dimensions, might be a little, turn off chur and DM, get those guys out of here. By default, it plots the 95% contour. And what that is 95% from the peak density here. So it's not 95% of the volume. That's going to be in the next version. And they actually do give you slightly different results if you think about it in a statistical sort of way. So here, this is just 95% from the top of the highest peak, which might not actually be as informative as 95% of the total volume of this bivariate KDE. You can add set contours, just split it up evenly by 3s. Maybe make it a color that you can see a little easier. So now we've just done an even split of 3. You can go kind of nuts with this. How about 14 different splits? And then you can see that it's kind of like a topo map, where you do the default MATLAB contours, which honestly, I don't know how they actually calculate those. So I like to I like to plot things where I know what's happening. So I tend to stick with either the 95 or a split of, say, your top, middle, and bottom 3 contours. For saving, I'll just spend just a second on saving. This is another thing I get a lot of questions on. And so you can imagine you want to make a plot like this, right, in a paper. I probably have an example. The paper that I actually published this in here somewhere. If you want to make a fancy plot, so how about, you want to make something like this. That's what you ultimately want to do. And I made these using this plotter, but unfortunately, because of the type of data that's being plotted, it's not as easy as a click of a button. And that's because the maps themselves, the color maps, are best represented as rasters. So you can think of it as like a digital image. That's a raster, like just pixels with RGB values. Whereas the lines are better suited for vectors. What that means is you need to export these results individually. And I'm working on a way to automatically do this for you, but it's just easier done manually. So basically what you do is take your map, you save the map, and you call it like map or something. Go to desktop. So save that, and what it's going to do is it's going to say, hey, only the map is plotted. I know to make this a raster. If you make this if it was forced to be a vector image, it'd be about 10 kilobytes. It'd be huge, and so it won't let you do that. So I put in some safety features column. If you wanted a scatter plot on top of that, you'd save that, and if there's no map, it's going to say, hey, I want to make this. Usually just call it scat. I want to make this a vector image. I'll also save that on the desktop. And this will become clear if you're not as familiar with vector and raster. But if you open up the map now, vector image, it's like a picture. You can't do anything to it. But what you can do, and the axes are not editable, it's just a picture, whereas the scatter plot, if you take this, I'm going to take everything. Actually, there's usually some extra stuff I don't need on here, but I'll take everything, cut it, and there's a great little function in Adobe Illustrator called paste in front. So lock that old layer, put the new one in there, and say Control F or Command F if you're on a Mac, and then delete that or make it clear. Now you have both. And you'll need to tinker with this because obviously you can't see the map here, but if there were fewer data points, then you'd be able to see both. But now you have a vector image here for your data points on top of that. And I know I went through that quickly, but in the program, if you click on frequently asked questions, I think that's the only question that I actually have answered in there is how do you make figures? And so if this doesn't make sense, just like all of these programs, just send me an email and ask me. Okay, so I have 5 minutes. And what I want to do is show you the next step. So we talked a lot about quantitative comparisons earlier for one-dimensional things, age distributions. They're just one-dimensional arrays once you make it into a probability plot or a kernel density estimate. But what if you could take 2 different intensity maps like these and quantitatively compare them? Is that possible? And the short answer is, what is that? The short answer is yes. And so I'm going to open up MATLAB here. And this code is not out there yet. It's still under development, but it works functionally enough to show you something cool. So I'm going to do that if MATLAB decides to join me here. While that's opening, I'm going to go find DZ Stats 2D. This is to be submitted soon. So, but if anybody wants the code, I'm happy to send it along. It's under development. DZ Stats 2D. So what this program is going to do is take the quantitative metrics that we talked about earlier and that we used in DZ Stats and DZ MDS, and it's going to calculate them in 2 dimensions instead of 1. And it turns out the math is actually quite simple to do this. And so what I've done is made an interface like DZ Stats. It's like if DZ Stats and Hafnium plotter had a baby. You think about it like that. And so what this is going to do, I'm going to load in some data because Hafnium plotter only plots 1 sample at a time, right? And so I always wanted to say, I want to objectively compare 2 samples or 3 samples or heck, take the whole global database, chop it up into pieces and compare that. So say I had 8 samples from 8 different, I don't know, regions. And say I specified regions, kind of going off the rails from what I decided to actually show you, but I thought this would be fun. Here's a map. Say I broke up the world into different regions. So North America, South America, Perigondwana, Asia, Baltica. Say I broke up the global database in that fashion and separated those data out and just looked at their detrital components. That's what I believe, or their combined detrital igneous. I can't remember what I have in here. But what we're going to do is plot now 8 little Hafnium plotter plots, and we're going to quantitatively compare that with the metric of our choosing. So here would be our 8 samples. Here we are plotting cross correlation, and it's automatically colored. You could say, well, I want George's metric, like or similarity, but in 2 dimensions. And that's going to show you what those values are, or say you like likeness. You can also look at this in a cumulative format, which is kind of crazy to think about at first, but if you just sum to one of the corners, now you're looking at, and Hafnium plotter doesn't do this, but you can actually do a KS test in 2 dimensions. And the math is, actually this math is surprisingly complicated for what a KS test in 1 dimension is. But at the end of the day, you get the numerical assessment of their similarity. You can plot this out, just like we did before. You have 8 samples versus 8 samples. You get a colored matrix for cross-correlation, likeness, similarity, KS. And just like before, you're looking for consistency. And you can also automatically just say, you know what, I want to look at this as an MDS plot. And it'll automatically do that for you. So this is where it's going, both more dimensions of quantitative comparison and just more user-friendly. So This new version will also have DZ-Stats 1D in it, if you want to call it that, so that you don't have to do all the steps we did in Excel earlier with conditional formatting. It'll automatically do that for you. So again, if anybody wants this to play around with, I'm happy to share code. I'm not going to put it on GitHub until it's in review, which should be, I think, next month. But just wanted to show you where this is all going. Yeah, because it's kind of fun stuff.